In this video, we will talk about the technique called real-time kinematic, or RTK. RTK is used to enhance the positioning accuracy of the GNSS. To learn about how GNSS positioning works, please watch this video. The link is in the description section. With an RTK-capable receiver, you can measure your position with centimeter accuracy. Therefore, such receivers are irreplaceable when it comes to land surveying and other applications where you need to know your exact position. Let's look at the signal traveling from the satellite to the GNSS receiver. On its way, it travels through different layers of Earth's atmosphere, including the ionosphere. This affects the signal's propagation and introduces some measurement errors that a standalone GNSS receiver can't solve. These errors reduce calculation accuracy. So a GNSS receiver can't provide positional data better than meter accuracy. RTK resolves these errors by using the second GNSS receiver located nearby. So a typical RTK survey setup consists of two devices, a base and a rover. A base receiver is static and placed over a point with predetermined coordinates. A rover receiver is movable, and that's the receiver we use for data collection. The idea is if we have two receivers close to each other, the atmospheric errors for signals they observe are almost identical. As a result, they can be excluded from the calculations. By eliminating these errors, a rover receiver can better estimate all ambiguities in its positional calculations. To do that, the base receiver transmits its position and observed satellites data to the rover. The rover uses this information to exclude atmospheric errors from the calculation and better estimate its position. Still, having a second device is not enough for achieving centimeter accuracy. Another essential part of the RTK technique is complicated mathematical algorithms. With these calculations, it becomes possible to achieve centimeter-level positioning accuracy. Let's look at what the RTK calculations consist of. First, there is the pseudo-range measurement. The pseudo-range is an estimated range between a satellite and a receiver. Knowing the time the signal was sent and received, the receiver calculates the distance to the satellite. However, the pseudo-range measurement is not a very accurate way to find the distance. This brings us to the carrier phase measurement. The carrier phase is a more advanced way of determining the distance between the satellite and the GNSS receivers. The radio signals from the satellites are traveling in sinusoidal waves to the receiver on the ground. With the carrier phase measurement, we can understand where exactly we are in the phase. However, to calculate the distance, we need to know how many full cycles there are between the satellite and the receiver. So, after calculating the phase, our goal is to count how many wavelengths there are. Knowing this number, and that each wave is about 20 centimeters long, we can calculate the distance between the receiver and the satellite. The process of finding out the number of full wavelengths is part of very detailed computations that go on inside the rover receiver. Once the pseudo-range measurements and carrier phase distancing have been calculated to several different satellites, it is possible to determine the receiver's position accurately. Let's see how it works in the field. As already mentioned, the RTK setup consists of two receivers. The first is the base receiver that's located over a known control point. The second is the rover receiver that's moving and collecting data. The base passes the information about its position and observes satellites' data to the rover over the internet or radio. This information is called base corrections. With these corrections and RTK algorithms, the rover receiver can exclude atmospheric errors and accurately calculate its position. The distance between base and rover is called the baseline. For single-band receivers, the recommended maximum baseline for RTK is 10 kilometers, and for multiband, it's 60 kilometers. While staying within these limits, we can assume that atmospheric conditions are the same and we have a reliable solution. It is important to note that you don't always need your own base unit for RTK. In most cases, there are local service providers who have their own base stations. These stations can share their base corrections over the internet through a technology called N-trip. To learn more about it, watch this video guide, the link provided in the description section. Thanks for watching.